Hello, welcome to the last lecture on nonlinear optics for this course. We were discussing, well, kind of extreme nonlinear optics, namely nonlinear optics in the strong field regime. Let me briefly review what we discussed last time. So we were discussing in particular high harmonic generation. So here I have the script from last time. So we have a spectrum with a very peculiar form. So what we discussed so far was, say, the third harmonic, or maybe the second harmonic. Of course, if we are talking about high harmonic generation in the usual sense, namely that we just shoot with an intense laser in a cloud of gas, then we don't have an inversion sender, and therefore we only expect odd harmonics. Okay, good enough. So we only expect odd harmonics, and so far we discussed only the third harmonic for this case. But now we see that we also have the fifth harmonic. Well, you could say then we would expand our power series expansion for the polarization just by two other orders. Well, if we would talk about the seventh harmonic, you would probably feel or start to feel quite uneasy, considering all the complications that we had to deal with. But then something spectacular is seen, namely that subsequent harmonics are no longer decrease, but stay fairly the same, and accordingly it's called a plateau. The plateau ends at some point, as one could expect, and this is called the cutoff. Okay, so this is a characteristic phenomenon of strong field nonlinear optics. In order to deal with it, we started by introducing the so-called atomic units. So everything that we discuss in optics is something that involves the electron cloud of atoms or molecules, and therefore the mass of the electron, the charge of the electron, but also the Planck constant. They are kind of the natural units we are dealing with, and accordingly we do everything in units of, say, the mass of the electron, the charge of the electron, and also of the Planck constant, more precisely speaking, the Planck constant divided by 2 pi h bar. Well, and then so this gives rise to new units, or to units of energy in these atomic units. So the atomic unit of energy would be 27.2 electron volts, which is just twice the ionization threshold of hydrogen, as you see here. Then for the intensity, we can also one can also derive that, and one arrives at an intensity of 3.51 times 10 to the 16 watts per square centimeter. This, by the way, corresponds to the same field strength that an electron on the first Bohrian radius would see. So the Bohrian radius is actually the atomic unit of length. This is 0.53 angstroms, or 0.53 times 10 to the minus 10 meters. And then we also have the atomic unit of time, which is 24 attoseconds, and 2 pi times 24 attoseconds would be the Kepler period. So the orbit period, if you believe the Bohr model, then this would be the correspondence of that. Okay, we were then discussing the parameter regime of strong field nonlinear optics. And we said that what we obviously need to do is to go a big step beyond what we did in nonlinear optics, namely that we disturb the electron a little bit, well, a little bit more than in optics, such that the harmonic approximation is no longer valid. So this was nonlinear optics. But now we want to make it extreme, and this means that we need to disturb the electron, say by an atomic unit of length. And we derived some equation for that, and this is actually the lower bound where extreme nonlinear optics would start. We invoked a few other parameters. One was the so-called barrier suppression intensity. If you think about a Coulomb potential that is distorted by an electric field, here a static electric field, and you would make this field so strong that the potential here is disturbed so much, so that this barrier here is below the ionization or the ground state energy of the atom, then we would speak about the barrier suppression intensity. So we would derive a field, which is quite easy to derive, and then convert this field into an intensity, and we would call this the barrier suppression intensity. And you can imagine if you really hit this intensity, which is actually not so high in terms of modern laser technology. It's depending on the ionization threshold, something like 10 to the 14 watts per square centimeter, even for most rare gas atoms. So if you hit this, then you can imagine that such an atom ionizes very quickly. So the electron is just free, at least for an instant of time. Another characteristic parameter, and perhaps the most well-known in this field, is the so-called Ponderomotive energy. Complicated name for a trivial thing. So we just do it like the medical doctors, right? So if they have no idea what a disease is about, then they give it a sophisticated name, and the patient thinks the doctor knows everything, is a good expert. Kind of the same thing here, right? Well, actually, we do know what we are talking about, but nevertheless, this quantity got a sophisticated name, namely Ponderomotive energy, which just means that it's the cycle averaged kinetic energy of an electron that is driven, of a free electron, that is driven by an oscillating electric field, right? And this can be quickly calculated. You just need to integrate the equation of motion once, then you have the velocity. You take the square of the velocity, and you take the cycle average, and that's it. And that's the Ponderomotive energy. And in atomic units, again, it follows a simple formula, namely, it is proportional to the intensity, and it is proportional to the wavelength squared. So if you want to know a simple equation in terms of SI units, then you could use the following. So 0.09337 times the intensity measured in watts per square centimeter times the wavelengths measured in meters, but the wavelength squared, of course. Okay, then another thing was connected maybe to the discussion here above. So I said that it's possible to just open kind of the door for the electron in order to just go out. Well, if you don't quite open it, such that the electron has to tunnel a little bit, then of course the question is, does the electron have enough time in order to tunnel? And this question, so is the door open for a long enough time? And this question is answered by the so-called Keldysh parameter that we introduced, and it is defined as the ratio of the tunnel time to the optical period. Yeah, so it indicates the longer the optical period, the longer the wavelengths, the smaller the Kaldish parameter, and yeah, so what's interesting here is the are small Kaldish parameters. Just to highlight kind of the opposing case. So if you have a free electron laser, then actually you can produce field strengths that are, well, that are close to what we have here or even exceed what we have here. But nevertheless, this is not strong field laser physics in the sense that we are doing, because the frequency of these free electron lasers is so large, well, that this door for ionization closes so quickly that, well, that the electron doesn't oscillate a lot. Well, you can also see a similar thing or another aspect of that in if you calculate the ponderomotive energy. If the frequency is very high, right, then this ponderomotive energy will be very small. So what we found here is that for typical parameters, yeah, so a visible or a near-infrared or even an infrared laser, short pulse laser with, say, 10 to the 14 watts per square centimeter, there you get a ponderomotive energy which is much larger than the photon energy. Yeah, so even in this case where we have an old-style titanium sapphire laser at 10 to the 14 watts per square centimeter, there we would have a ponderomotive energy that equals 4 times the photon energy. And we could also produce 10 to the 15 watts per square centimeter, and then we would have 40 times the photon energy. Okay, well, a final thing here, which we kind of had already. Yeah, so we were calculating over here the amplitude of the oscillation. And we derived this intensity, which I said is the minimum. But now we could say, well, if we calculate the amplitude, the oscillation amplitude, for relevant intensities, yeah, so for intensities where we found that the tunneling rate becomes significant, yeah, then we would substitute into this formula 10 to the 14 watts per square centimeter and just would calculate how big this oscillation amplitude is. And I would like to write that down. So the oscillation amplitude for typical parameters Yeah, so typical intensity and a typical laser frequency. We found that the oscillation amplitude in atomic units is given by the amplitude of the electric field divided by the frequency. And now, if we do an example, namely 800 nanometers, then we know that, well, that these 800 nanometers correspond to 1.55 electron volts, right? This we divide by 24.2 electron volts. Then we have the energy in atomic units, but the energy in atomic units equals the frequency in atomic units, because the energy of a photon is h bar omega, and h bar is equal to 1. Yeah, so what we get here is 0.057 atomic units. For the intensity, we use 10 to the 14 watts per square centimeter. And for this corresponds to an electric field of 0.053 atomic units. So almost the same number. And what you see is that omega goes in with the square. And you immediately find, so you have the inverse of 0.05, which is kind of 20. So what we find is A naught equals 0.053 divided by 0.057 squared, and this is roughly 20 atomic units. So which means 20 times the Bohrian radius. So quite interesting, because there you see that the Coulomb force that is still pretty strong at the first Bohrian radius is much smaller at this radius of 20 atomic units. And this insight will actually be important for what follows. Okay, so people tried to get to get a handle on these new effects, and because people for many years were trying to understand multiphoton processes in the way that we discussed, they were a little bit puzzled, and this was in the beginning of the 90s. And so what they did at some point was just to solve the Schrödinger equation numerically. So computers were powerful enough around that time. A few years later, I was even able to do such calculations on a PC at that time. Well, it took many days, sometimes weeks, to get a result. But what people did at that time was to solve the Schrödinger equation numerically. So solving the time-dependent Schrödinger equation, which means we won't solve it here, of course. But nevertheless, to tell the story of this field, I think it's absolutely necessary to also say a few words about that. So what's solved is the Schrödinger equation, so not the kind of Schrödinger equation that we dealt with when we were talking about the propagation of short pulses, but this equation can be solved numerically. There are different means, and what you would get is the wave function of the electron as a function of time, right? So, and so you immediately know what you now can do is to calculate where the electron is, or the probability at least where the electron is, and this will be time dependent. And now you know from the second semester electrodynamics that an electron that is accelerated will radiate electromagnetic waves. And in order to calculate that, one has to compute actually the time-dependent dipole moment. So the second derivative, which corresponds then to the acceleration, right? So where this d is given by x times e. So if we consider a one-dimensional motion of the electron, so if the electric field oscillates back and forth in the x direction. Okay, so once we have that, we would do a Fourier transformation. So the next step would be compute the Fourier transformation of the above, and then we would just look what comes out, right? And the first, to my knowledge, the first or one of the first who did this, actually they did it already in 3 dimension. This was Ken Kullander and Ken Schaefer So Ken Kullander became ill a few years later and had to leave science. Ken Schaefer is still very active at Louisiana State University. Jeffrey Krause I never met. He probably was a PhD student at that time. So they did these calculations and calculated the harmonic spectra along the lines that I just outlined here in a very rough sketch, right? You see this here. So in this case for helium, and here they did it for for different intensities, and you see here this plateau that extends out to 400 EVs or so, right? So, and this gave an insight, namely that the end of this plateau, so the cutoff, that this has a very simple, that this follows a very simple scaling law. So I copied this directly from this paper. So the plateau extends up to 3 times the Ponderomotive energy plus the ionization threshold, right? So you can check this. So 527 nanometers gives, of course, a little bit different Ponderomotive energy, 10 to the 15 watts per square centimeter, actually 5 times 10 to the 15 watts per square centimeter. Okay, a very simple law, but the question is, can we understand it? And the other thing that was not covered at that, or at least not in that paper, was that this is, of course, just the single atom response. And in a cloud of gas, you have, of course, billions of atoms, which each emits, well, a spectrum like that. The complication is that if you have a Gaussian focus, the intensity at each point is different, right? So each produces a little bit different spectrum, each atom. And you have to add them coherently. You have to see whether all these atomic emitters, whether they emit in phase or not. So whether there is phase matching. So so this is just the microscopic, the atomic response. What you also need is the macroscopic response. And this they did a little bit later. So you see the same authors on the theory side, but you also see Anne Lullier, who first of all discovered high harmonics, but she also made major contributions to pretty much, or to most of the things that followed in the business of high harmonic generation. Okay, so the question was now, how can we understand? How can we get a picture that's more helpful than just a numerical calculation that takes hours, or at that time perhaps even days, in order to complete? How to get an intuitive picture that could help us to find ways so the interesting approaches for new ideas. Well. And if you consider what we discussed above here, so in the preceding paragraph here, where we talked about parameters, we were pretty much talking about classical oscillation of this amplitude. We were talking about the Ponderomotive energy, so an electron, like a particle, a massive particle that oscillates, classical particle. So the only thing that was not classical was perhaps the tunneling probability, but that's it pretty much. So trying with a classical model Yeah, so this was one thing that people did at that time, and of course there was a lot of opposition against that because as a real physicist, you believe in quantum mechanics, right? But on the other hand, in physics we also know that that there is a transition from the macroscopic to the microscopic world. We even know systems that kind of represent this transition, most notably Rydberg atoms. Yeah, so where you have an atom in a very highly excited state, and of course there you can also learn and understand some fundamental properties in terms of classical concepts. And so people were starting to do the same thing here. And I would like to quickly describe this. It is known in this field as the three-step model of high-harmonic generation. And interestingly, a few years later, then quantum versions of this three-step model were developed. So the three-step model, in names like Paul Corkum, I should have prepared here a slide with his paper, with his seminal paper. So people, and also others, so even Kullander and Krauss and Schaefer contributed to these things. Actually, myself too. So, but anyway. So, the three-step model, and perhaps I should add here another headline. We could also talk about what's called the strong field approximation. Yeah, so there are different opinions what to understand under strong field approximation. I will provide you my version of what it is. Okay, so the three-step model consists of, guess, 3 steps. And the first step is actually outside this classical model that we want to develop, because the first step is the promotion of the electron from the ground state into the continuum. Yeah? More specifically, we assume that this happens, that this first step happens at a specific instant during the oscillation of the electric field. Yeah? So the first step is promotion of the electron from the ground state to the continuum. And the important thing is, at a certain time, at a certain instant, which I like to call T0. Right? So if we depict here an oscillating electric field, say like this. So here we have an electric field, and you see this time T0 here already. And the sketch for the transition to the continuum could be this one here. Right? So you see this this potential here, so that oscillates back and forth like this, right? And at some time, say at T0, the electron goes to the continuum. And this is a quantum mechanical process. We can't, in the framework of a classical model, we can't say much about it. But of course, we have an idea. It could be tunneling, right? So we assume that at some time T0, the electron tunnels out. Of course, if it is tunneling, then the probability that it comes out is highest at the peaks, right? But of course, there's a certain probability that it tunnels out here or here or here. And what we'll do is that we study things as a function of this time t0, right? So this time t0 is kind of the parameter. So this is the first step, so which means that we have an electron that has tunneled out. So it sits in the vicinity of the atom. After tunneling, it has velocity 0 and sits pretty much where the electron is, right? So we could say that the velocity at t equals t0 is, to a good approximation, equal to 0. And we can also say that it sits at this position 0, right? Okay, so this was the first step. The second step is propagation in the field. And now actually we could already discuss this in terms of what the strong field approximation says. So strong field approximation, this is a typical example where a physicist says 1 can be large as compared to 1, and 1 can also be small as compared to 1. Let me explain how this is meant. So talking about this time t0, so before this electron was promoted to the continuum, we kind of assume that it's so tightly bound that, well, that not much happens to the electron. Yeah? So as long as the electron is in the ground state, it is in the ground state just, right? And we even assume that not much happens to this ground state. Yeah, so what could happen, of course, would be that this ground state is shifted a little bit up or down or whatever, right? So quantum mechanics certainly would describe that, but we neglect that. Yeah, so for times t equal t smaller than t0, we neglect the action of the electric field. And for times that are larger than t0, so after the electron has or was promoted in the continuum, we do just the opposite. We say that the electron is more or less free, and we neglect the atomic potential because the field is so strong, right? So you see that these are bold approximations, but, well, if it helps, yeah. Good. So propagation in the continuum. Yeah, and the approximation is the electron is more or less is a free electron. Yeah, so what we have then for the second step would be the following. So again, our oscillating wave here, and we would follow our electron. So from this, so this electric field, this determines the trajectory of the electron. And in order to show a few trajectories, here this sketch here, so I have drawn 2 of them for 2 different times t0. So when we have a time t0, like the one that is shown here, the trajectory, at least qualitatively, would look like this, right? So the electric field is in this direction, right? And here I depict the velocity, say, right? And so here it goes in negative velocity, right? And then the field changes its sign, so it's accelerated in this way, right? So it will travel, it will be driven out away from the atom in this way, right? Now, if instead of this time t0 we would have this time t0, then actually such a trajectory would evolve. Okay, well, we said that we neglect the atomic potential, and therefore it is of course quite easy to calculate these trajectories. Now, let us do that. So we have the equation of motion. So m times the acceleration equals, so this is Coulomb's law. And what we assume is, for the sake of simplicity, we assume a constant amplitude. We assume an infinitely long pulse. But actually, we just are interested in one optical cycle. So whether this pulse has, or perhaps 2 optical cycles, so whether this pulse has 10 optical cycles or 10,000 doesn't make any difference for this kind of analysis here, right? Then we can, of course, integrate that and get the velocity, the time-dependent velocity, right? And of course, we need to look at the boundary conditions, namely, or the initial conditions. So what we get is sinus of omega t. If I integrate the cosine, I get the sine, right? And in order to satisfy the initial conditions, I have this term. And you immediately see, if you plug in here t equals t0, then this thing is, of course, 0. And therefore, we satisfy these initial conditions. Okay, if I want the trajectory, well, this here would already be good enough in order to calculate the cycle average energy. So the photoelectron kinetic energy that I would measure if I'm interested in the photoelectron, right? Anyway, yeah, so if we do photoionization, as we do in my group, for example. So we integrate once more, and we get the position as a function of time. And of course, we need to use the chain rule once again. So we have omega squared in the denominator. We know this expression already. This was the oscillation amplitude. Now we have cosine of omega t minus cosine of omega t0 minus same thing here, and then omega t minus omega t0 and the sine of omega t0, right? And you can just plug in t equals t0 and check whether x of t equals to t0 is equal to 0, and it should be. So this would be equation 10 and 11. So now, some of these trajectories are more interesting than the others. And if you look at these 2 trajectories that I have drawn here, and if you think about what you want to do, namely to create harmonics and not just look at photoelectrons, then you certainly agree that a trajectory like this is more interesting as compared to a trajectory like this, because this trajectory here returns to the vicinity of the electron. And so actually, what I should have mentioned is that these trajectories here are not to scale. Yeah, so we said, interesting snow outside. We said already that the amplitude, and this is kind of the amplitude, the oscillation amplitude, that this would be 20 times larger than, so then kind of the size of the atom. So this would oscillate here, quite a lot. Okay, so something happened here. Interesting. I'm a completely different document. Okay. So the third step would be recombination. So let me depict here or show a graph where kind of this situation here is enlarged. But first, let's write third step. The third step would be recombination. Recombination. So for certain trajectories, for certain T0s, the trajectory returns to the vicinity of the atom. Right, made a long excursion, right, returns to the vicinity of the core, and then the electron may recombine, right, may recombine to the ground state, right, and release a photon as I indicated here. Okay. So recombination upon return at some time t equals to t1. Right? And now the question is, with which energy will this electron here return to the vicinity of the core? Right? We can calculate that. It's a little bit more complicated because what you have to do is to set the boundary condition that x of t equals t1 is 0 again. Right? So what we have is that x of t equals t1 should be 0 once again. Right? And then at this instant t1, we would calculate, we can calculate then the energy E1. So the instantaneous kinetic energy when the electron hits the atom once again. So which is equal to E at time t equals to t1, which is, of course, 1/2 m mass, x of t1 squared. Right? So this thing we would calculate. And we would calculate this as a function of t0. Right? For each, now a thunderstorm. So for each t0, you get a different return time. Well, there are a few T0s for which there is no return time, as you have seen here, right? So this never returns, right? But for all T0 in this quadrant here, so in this quadrant here, they will return. And they will return with different velocities, right? So two limiting cases. So let's enlarge this here a little bit. So if the electron comes out just before the zero crossing at pretty much zero electric field, then you find that the electron returns pretty much, so it has a very short excursion time. So it will have zero return energy or very small return energy. On the other hand, if the electron comes out here, right, then it makes the full excursion, gets accelerated a lot, but is fully deaccelerated by the next half cycle. right? So it also, an electron that comes out here will also return with 0 velocity, right? So, and then in between there should be a maximum, right? And most easily this is done numerically. And what one could do is to plot E1 as a function of T0. Yeah? And if you do that, then you get a figure, like this. Yeah, so just look at the red curve for the time being. And what you find here is, well, if the electron comes out at the maximum of the field, then it will return after a full optical cycle with 0 velocity. If it comes out, so you see here a quarter of an optical cycle, so 0.25, right? So T, capital T is the optical cycle. Then it also comes back with 0 velocity immediately, right? So here it has a long travel time, here it has a very short one. But of course the interesting point is here in between, for some T0, so 20% or so of the oscillation period, we get a maximum. And now look where this maximum is. So this maximum turns out to be pretty much at 3 UP. More, of course, you can calculate it precisely. It's 3.17 UP. 3.17 UP. Yeah? And once this was understood and discovered, this law that I just showed from the paper of Kullander and Schäfer, yeah, so this number of 3 UP was changed to 3.17 UP. Yeah, 3.17 UP, this is the maximum kinetic energy that you can get here, right? And because it recombines, you also get the ionization energy on top of that. Yeah? So this is a nice thing to do yourself. Yeah? So use MATLAB or Python or whatever you want to use and try to reproduce this graph here. You learn a lot of, yeah, so it's simple physics, it's high school physics, but you learn a lot about strong field laser physics. Okay, we are not yet done, as I indicated, because we now, so far we just have looked at the response of a single atom. So this is what a single atom does. So what we also need to look at is phase matching. And phase matching is actually kind of complicated here. Actually, to be honest, when we looked at phase matching, say, for second harmonic generation, we also made things easy. Yeah, so we made approximations. We didn't consider that we typically have a Gaussian pulse with a Gaussian intensity distribution. Yeah, so we considered the laser pulse a plane wave. Of course, for strong field laser physics, this is not a reasonable approximation, and therefore one has to consider the more or less full complication right away. And there are actually 4 contributions to phase matching. So let's write a headline, 17.4, phase matching of high harmonics. Yeah? And there are actually 4 contributions and 1 boundary condition. So there are 4 contributions to phase matching. So 4 different effects that influence phase matching, plus 1, I call it boundary condition. Perhaps you find a better word for it. Let's call it a boundary effect. Yeah? So the first one would be the so-called Guri phase. Yeah, so it's written like that. Yeah, so Guri was a French physicist in the 19th century. Some people write him in this way. Right? So you find that frequently in the literature, but this is wrong. And it was the famous book of Siegmann on lasers. Yeah, so he consistently wrote it in this way. And actually, I remember he came once to my lab, when I still was a PhD student or a postdoc or so. And I was supposed to explain to him what I'm doing. And on the poster, I also had written down the Guri phase. And I wrote it incorrectly. And so he smiled and said, I see you have you have read my book. And I was puzzled, and his answer was, because you also write Guri in the wrong way. Okay, anyway, the Guri phase. So what is the Guri phase? Let's draw up here a Gaussian pulse. So I have a Gaussian pulse here. Nice figure, stolen from Wikipedia as usual. And now the point is that if you would propagate a plane wave in parallel to this focused wave, then you see that this that the phase of this focused wave advances quicker than the plane wave, right? And therefore, there is a phase shift with respect to a plane wave, like this. Which, for a simple Gaussian pulse, is an arcus tangens. Yeah, so arcus tangens z. Yeah, so if the propagation distance here is z, and we have a confocal parameter which is called z0, then this Guri phase follows the arcus tangens of z over z0. Z Rayleigh I've written here, and this ZR is given by pi over the waist squared times n is the refractive index, doesn't matter, and the wavelengths. Yeah? So the Guri phase. So what you should understand here is that if you have many atoms here, each of them is excited by a different intensity, but also by a different phase. Right? Okay, so second thing would be the phase of the wave function psi. Right? So we said that this electron makes this trajectory, eventually returns to the vicinity of the core, and then you suddenly have to say, well, it's not all classical mechanics. The electron is a quantum object. So it acquires a certain phase, and its phase is given by the classical action, right, divided by h bar. So the phase of psi, and this is the classical action divided by h bar, and the classical action, you know, from classical mechanics. So what we have to do is to integrate the Lagrange function, right, over dt. Yeah? And actually, this classical action is here, this curve here. Right? So you can easily calculate that also just by doing classical mechanics. Yeah, so this classical model is not so innocent and so wrong as it might look like, because it is just the limiting case of what's of an alternative formulation of quantum mechanics that goes back to Richard Feynman, so the Feynman path integral. So we see here a trivial version of that in some sense. Okay, so this is the phase here of psi. The next thing would be that we have, of course, the refractive index of the gas. So this is what you probably would have mentioned first, because it's the most obvious thing of the gas. So this won't be much, just the refractive index of gas is small, but we ionize these atoms, right? So therefore we also have free electrons. So the refractive index of free electrons. So, and then we have this complication. What you also need to take into account that we produce XUV radiation, and XUV radiation has a photon energy so high that you can ionize all matter. So every atom, if you have a photon energy that is beyond 24 electron volts, then you can even ionize helium. And therefore all the other rare gases and all the other atoms in the periodic table too, or the molecules, right? And this means that such photons are quickly absorbed. So there is reabsorption. And if you want to produce a lot of harmonics, then you kind of have to find a clever way on how to arrange things that, well, that enough photons survive for reabsorption. Reabsorption. Yeah, so, well, there are other things to consider. Namely, once the electron is gone, so once it is ionized and has flown away, then it won't be able to recombine. So ionization is nice, but too much ionization is not so nice. Right? So what you need to do is to try to make things quick enough such that perhaps only one optical cycle does the entire thing. So short pulses are really useful, because you can do things before the atom is destroyed. So short pulses help. So there's one thing that I also would like to quickly discuss. So you have seen that we create these harmonics. So typically, in 3/4 of an optical cycle or so. So at least below one optical cycle. And you have seen that electrons that come out here, that they are able to make harmonics. But also, of course, electrons that come out here, will be able to produce harmonics. In the same way, electrons that come out here will produce harmonics. So in other words, what we have is photon emission with a periodicity that's twice the optical period. Yeah, because it happens twice the optical period. That here we produce harmonics and here. So twice the optical period, and not just here and say here. I hope I didn't explain it in the wrong way. So not just here and here, not just here and here, but also here. And of course also here, right? So which means that photons are emitted with twice the periodicity of the optical field. And if you take the Fourier transform of that, then you find that this corresponds to, that this produces a separation of the harmonics by 2 omega, right? So this is another explanation of the fact that we produce only odd harmonics. Good, yeah, so just a different way to understand the same thing. Okay, so that's it. Yeah, so there are a lot of additional things that I could explain about that. But as I said already, this is enough in order to fill an entire course, and we will do so. And I hope the one or the other of you will attend in the summer semester the course on strong field laser physics. Good. Let me explain a few things that go beyond that. Yeah? So we were talking about strong field physics. We can make it even more extreme by going to relativistic intensity. And also there you would observe harmonics. So what you could do would be to just use a very intense laser, so say 10 to the 19 watts per square centimeter, a laser intensity that is strong enough to accelerate the electrons to relativistic velocities. Right? So what I did so far was non-relativistic. So if you use such a laser, and you shine it now not on a cloud of gas, but you shine it on a piece of glass, not gas, but glass. Yeah? Then you ionize the material there, you produce plasma. And plasma, of course, consists also of free electrons. So you would shake these electrons back and forth, and because you did it with a solid state material, the density of these electrons is so high, yeah, so the density of the plasma is so high that it reflects the light. Yeah, it's the same thing that happens in a mirror. So you use your laser in order to create a mirror. The mirror is actually shaking back and forth with relativistic velocities, and therefore what comes out is modulated. Well, probably not in this way. Here's a cartoon of that, right? So we have a relativistically oscillating mirror. And again, it's pretty easy to calculate these things. Yeah, so you have here the plasma mirror position in the lab frame and also in the local frame. Right? Here the plasma mirror velocity, and here you see the incident and the reflected field. Yeah, so the incident field is the faint curve, and the reflected field looks like, yeah, pretty much So under these conditions, a square field, and of course it has a lot of harmonics, right? So therefore, such a mirror also produces harmonics, high harmonics. Yeah, so this kind of stuff was calculated and investigated. I also did this a few years ago. And the huge advantage of this approach is that it has no upper limit for the intensity that you could use. So remember, for the gas harmonics that we discussed so far, if the intensity is too high, then you just ionize the thing, right? So the generation of harmonics saturates at some point, at some certain intensity, so that it doesn't make sense to apply more intensity. Yeah, so you can work against it a little bit by using a shorter pulse, but of course also this has limits. So this is not the case here. Yeah, so you can drive the intensity arbitrarily high. But on the other hand, there are also some disadvantages, some major disadvantages. Namely, yeah, so, that it is actually not so easy to to engineer conditions that happens such that things happen just the way as depicted here, right? In particular, things that can happen is that the light pressure actually pushes into this plasma mirror, and that things don't look so nice as depicted. The other thing are just technical problems, like you destroy your piece of glass. So for each laser shot, you need a new position on your target, and this is, of course, a major technical complication. And therefore, these relativistic harmonics are a promising source of XUV radiation, of coherent XUV radiation, like the gas harmonics. But I like to phrase it in the following way. This is a promising source since more than 30 years. Yeah? And time has to show whether the time of these relativistic harmonics will come or not. Okay, what can we do? And now I come for the last, 15, 20 minutes to some research that we are doing in my group, and that has to do with strong field laser physics. So the first example that I want to show just fits perfectly to gas harmonics. So we are actually using these gas harmonics in order to do what's called coherence tomography. What you see here is a coherence tomogram of a piece of silicon into which we buried 2 layers of gold at a depth of 200 and 300 nanometers. So this here is a depth of 200 nanometers, and this here is 300 nanometers. And just by measuring the reflected light, so the interference structures in the reflected high harmonics, we are able to retrieve the structure of the sample without cutting it into pieces or things like that. Yeah? I would like to, so here you see the same thing animated, right? And actually we discovered that there's more in the sample than designed, and we verified that actually our method did the right thing. So what is coherence tomography? Coherence tomography is actually known, or the most widespread application of coherence tomography is at the ophthalmologist's office. Yeah, so if you go to the ophthalmologist and you want your retina examined, then a modern ophthalmologist's office would use optical coherence tomography for that. So which is a fairly young technology, just 30 years or so old, but a market of billions already. They do it, of course, not with XUV radiation, but with visible, actually, with near-infrared light. And what you see here is a cross-section of a retina. Actually, it's my retina. And so I went to a local ophthalmologist, and so after saying hello, he asked for the reason that I came. And I said, I would like to have an OCT. And he was looking at me. He didn't know me at that time, and said, "Wow, why this?" And I said, "I need it for a lecture." And so for a lecture like this. Okay, well, it's a healthy one, so I can show it. How does it work? So this is the important point here that I want to make. So if you think about a retina, then it's a layered sample. If you think about this silicon sample where we had buried some gold layers, it's also a layered sample. And now OCT is most easily understood, has nothing to do with nonlinear optics, by the way. So the only thing that has to do with nonlinear optics in our case is how to generate the radiation. Okay. So OCT can be easily understood if you think about, so what you need is a broadband spectrum. So high harmonics offers a broadband spectrum. So it's kind of white light interferometry. And the easiest way to start this sentence for a third time, the easiest way to think about is that you produce a short pulse. A short pulse means a broad spectrum. So now let's here use a short pulse. You see that we have kind of a Michelson interferometer where one of the mirrors is replaced by the sample. And because it's layered, we have a reflection on each of these interfaces. So you see that this reference path made this one here shown in blue. And because we have a reflection here at the surface, then at the first interface and at the second interface, we have 3 replicas of that. And now we can do this, the following. We can move this reference mirror, and then you see that when they overlap, we get, of course, interference. And if they don't, we don't get interference. Actually, you don't need a short pulse. You just need a spectrum with a short coherence length, right? And then you see, of course, that this interferogram reflects the depth structure of this sample, right? So this is OCT. I hope you have learned something interesting now. Okay, so this is one of the things that we are doing. So using high harmonics for imaging, for nanoscale imaging. So the other one is that we do actually photoionization, so that we look for the photoelectrons that are produced, and we even use also this effect in order to measure something. So what you see here is a very short pulse. We call it a few cycle pulse because it consists just of a few cycles. And the tricky thing about such a short pulse is that, so that the shape of the electric field changes when you use a different phase, right? So we have the same envelope, but we have completely different electric fields. And the question is, of course, how can I measure that? And we devised an instrument for that measures this. So it's called carrier envelope phase. So this is here the carrier wave, the red curve, and the gray one is the envelope. So, and you can define the carrier envelope as the phase difference between, the phase of this carrier at the maximum, say, of the envelope. So it's just a definition, convention. Right? And the question is how to distinguish a pulse where the maximum of the electric field coincides with the maximum of the envelope, or a field where, say, the zero transition coincides with the maximum of the envelope, right? So to know that is extremely important, because in strong field laser physics, everything has to do with the shape of the electric field, not with the shape of the envelope. Well, and what we use is actually the twin effect of high harmonic generation. So for high harmonic generation, we had the thing that the electron returns to the vicinity of the atom and then recombines. What could also happen is that the electron, well, returns, but instead of recombining, it may also rescatter and absorb more energy from the field. And then you get highly energetic electrons, actually an effect that I discovered in my PhD work. And you can produce electrons that have a velocity of up to 10 times the Ponderomotive energy. Again, you can simply calculate this with classical, so with a classical model. And as I said, I encourage you to do it. And what we did now was to use a laser and ionize some material here in this gas cell. It has holes so that electrons, photoelectrons, can fly in opposing directions, right? And we are measuring these electrons that have rescattered, so they also form a plateau, but in the photoelectron spectrum. And if one does that, one can measure this phase with high precision. Quite interesting. When I discovered this effect 25 years ago, I never thought, more than almost 30 years ago, I never thought that it would have a technical application, but it has one. What we do, so our most sophisticated experiment is the following. We ionize actually ions. So we create specific ions. So simple stuff like argon plus or xenon plus or things like that, but also molecules, H2 plus, or even helium H plus. Helium H plus, a particularly interesting molecule. If you know a little bit of chemistry, you might say, well, helium H plus, does it really exist? Well, actually it does, and it's the most stable molecule in the universe, and therefore it was the first molecule after the Big Bang that has formed. But of course, it exists only as an ion. If you offer an electron to it such that it neutralizes, then it will immediately dissociate, right? But as long as it is a molecule, it is very, very stable. And we can produce this here just in an ion source where we have a high voltage discharge in an atmosphere of helium and hydrogen, and then this is automatically generated together with other products. But we can filter that so that we have a clear initial state. And then we have a beam of these ions, and we intersect it with an intense laser, and we look which kind of fragments are detected on a detector, right? And this detector here is a very sophisticated one, because it is position and time resolving, such that we can reconstruct the momenta of all the particles that are involved. So this is how it looks in the lab. And this is one example of a measurement. So the 2E's. So here we ionized neon plus. So simple stuff here, atoms instead of molecules. The laser polarization was perpendicular, right? And what you see is that the electrons, that they go in the direction of the polarization. Then the other case, the other extreme here is circular polarization, right? And what you find is, well, that the electrons are on a donut-shaped distribution. Yeah, quite interesting that you find none at 0 velocity, but all at a certain velocity. Well, actually, the radius of this ring corresponds to the Ponderomotive energy. Yeah? And now you take elliptical polarization. And the interesting stuff is that the major axis of the ellipse is here in the vertical direction. But you find most of the electrons almost perpendicular to that. And again, there's a very simple explanation for that. And this will be part of the course on strong field laser physics next semester. We can also ionize the ion twice. Yeah, so neon plus is ionized twice. So we find neon 3 plus. Right? Linear polarization. So the scale here changed a little bit. And now you find here these 4 half-moon shaped things here. What is the explanation for that? A beautiful one. Yeah, so the outermost, for this one here and for this one here, both electrons went in the same direction, and therefore the ion that we measured got a pretty large recoil, in quotation marks, right? And for those here, for those inner rings here, or for those inner maxima here, one went in one direction and the other in the other direction. You might ask, why didn't they compensate each other exactly? Well, the reason again is simple. Because the first electron went out first, yeah, so therefore I called it the first electron, and the second electron a little bit later, but a little bit later the intensity was larger, and therefore the second electron had a larger velocity, yeah, and therefore both momenta of both electrons, they didn't compensate. Good. Finally, something really remarkable. We can also do nonlinear optics with vacuum, and this is the third project within my group. Why can we do that? Well, the point is that vacuum is not as empty as the name suggests. Rather, vacuum is a process where you constantly create pairs of positrons and electrons, yeah, so anti-electrons and electrons, which after a very short time annihilate again. Right? So now if you use a strong laser, you kind of manage to align these electron-positron pairs that are created all the time and disappear quickly. Right? So you have aligned charge pairs. And this means that they become birefringent. And this is what we want to probe in order to learn more about the vacuum. It turns out that the best way to probe it is to use X-rays, because what you need to do in order to detect birefringence, yeah, so it means that the phase is a little bit shifted, right? And if you have a short wavelength, then a small shift in phase has a lot of effect on the polarization state of the field. Right? Okay, so therefore, X-rays. So the experiment is entirely classic. Yeah? So what would you do in order to measure birefringence? Right? A classic experiment in the second semester. Right? So you take 2 polarizers in cross position, right? One like this, one like that. If you would try to look through it, it would be entirely dark. And now you put something in between of which you want to measure the birefringence. So classic is a crane hook made of plexiglass that you stress a little bit, and then you can actually see where this crane hook is stressed most, so where the material would break first. Yeah? We don't stress crane hooks here, but we stress the vacuum, and we stress it by an intense laser. Right? So now we have here vacuum that became in this focus of this petawatt laser, say. Right? So we align these pairs. And now we probe it with an X-ray beam. And in order to make it very sensitive, you need a lot of photons, and you need them in a short time, because this petawatt laser also has just a duration of a few tens of femtoseconds. So you need a free electron laser that is also short pulsed and has a lot of photons per pulse. And of course, you need X-ray polarizers. And now you might think, well, X-ray polarizers, are there good ones? Well, actually, the best polarizers are X-ray polarizers, and the best X-ray polarizers are made here in Jena, in my group, and they are actually quite simple. Yeah, so this one here consists just of a piece of silicon into which a channel was cut. Therefore, these polarizers are also called channel cuts, channel cut crystals. And what you do is that you reflect the X-ray beam by 90 degrees. Yeah, so you choose the X-ray energy such that the Bragg reflection happens at an incidence angle of 45 degrees, such that you get a deflection by 90 degrees, right? And that's another classic experiment from the second semester. Do you remember the experiment where we shine a beam of light through a tank of water in which some milk or so is dispersed, such that we see scattering? And we show this experiment typically in order to demonstrate that the blue wavelengths, so in order to demonstrate Rayleigh scattering, so that the blue light is scattered more than the red light. So you would see from 90 degrees, you would see the bluish light, right? And in transmission, you would see a reddish light, which explains why the sky is blue, and which also explains the red colors at sunset or so. But the interesting point is, of course, or the other interesting point is that the light that is scattered, so this bluish light, that this is polarized. Why? Well, if you look at 90 degrees, so the incoming light can be polarized in this way or in that way. And now if you look at light scattered at 90 degrees, it can't, of course, polarize in horizontal direction any longer, because it would oscillate in propagation distance, which is incompatible with the fact that electromagnetic waves are transversal waves. Okay, so we use the same thing here. We scatter, or we reflect by 90 degrees, and so at each of these reflections, the polarization purity becomes better. And if things are done right, then a polarization purity of 10 to the 11, or perhaps even 10 to the 12, can be achieved, which means that only one photon in 10 to the 12 photons has the wrong polarization, right? And this gives the required sensitivity in order to measure very, very small birefringences, such as the birefringence of vacuum polarized by a strong field. Yeah, so this is a very, well, I wouldn't say esoteric, but it sounds a little bit like that. So this is a very peculiar form of nonlinear optics, and certainly a good point to close this lecture and also this course. Thank you for your attention. I wish you all the best, in particular also for the final. Thank you.